So, under the alkenes, when one double bond is there, we are calling as the alkenes, but under the alkenes we have a small extension, that is alkadienes. So, these properties of alkenes are over in fact. So, we can take alkadienes. Dienes means two double bond containing compounds, isn't it? So, with reference to the position of these two double bonds, we can divide the alkadienes into three types. First type of diene is whenever a double bond is there, another double bond is alternatively one double bond, one single bond, one double bond. This type of double bonds are something special, very important also. They are called conjugated double bonds. Conjugated dienes, you can say conjugated dienes. And there are some double bonds which are attached to the double bond, one more double bond attached, double bond attached to double bond, second equality. This is called cumulated double bonds, cumulated double bond, dienes. And third variety will be, there will be a one double bond, a minimum of n is equals to not 0, 1, 2, 3, 4 and so on. After that, another double bond is there. One double bond and another double bond is separated in fact. One double bond and another double bond is separated by a CH2 unit. In such a case, this double bond cannot influence the other double bond. So, the preparations and properties will be just like on par with the alkenes. So, this will have a called isolated, the name is isolated dienes, isolated dienes. This shows their properties will be something exactly equals to the ene into 2. All alkene properties double. One ene absorbs one molecule, means two enes are there. So, two molecules of bromine will be absorbed. All properties, ozonolysis, everything will be common like alkene. So, therefore, this is not at all important, that is isolated dienes are not important. And cumulated dienes have one property, these hydrogens will be shifted to the other side and they undergo a process of tautomerization and will give the propyne. Propyne and accumulated diene, the electrons will come here, this will shift here, the proton will go there and you will get the, this will become that, that will become this. So, the accumulated dienes are known as, here in this case, specially case it is known as alene. Alenes are unstable. Immediately they become into the propyne, alkynes. So, if you read the properties of alkynes, okay, the alene is unstable, therefore it gives this one. But alkenes, alenes, if you have substitutions rather than hydrogens, instead of hydrogens, if alkyl groups are there, then they are stable. Specifically, if the alkyl groups are there, they are able to show even optical isomerism also. Even monosubstituted alkyls also shows optical isomerism. Then coming, this is a changes to alkane, therefore, this property also not necessary to read. Conjugated dienes are having the special properties are there. This we are going to see in detail, and some preparations not much important, but its properties especially we have to read the properties of this conjugated dienes. So, the properties of this conjugated dienes. First property is they show resonance and thereby they get stabilized. So, we can say resonance stabilization or stability. So, conjugated dienes show this specific phenomenon called resonance, because under the resonance topic we have seen under what condition resonance comes, means one double bond, another double bond is in conjugation. This is called pi-pi conjugation. Similarly, a double bond and a lone pair of electrons conjugation, pi-p, a double bond and a charge, pi charge. These are the three conditions eligible to show resonance. We have first equality, that is pi-pi conjugation is there. So, let me write the smallest molecule, that is 1,3-butadiene. Its name is first carbon, third carbon enes are there, therefore you call it as a 1,3-butadiene. This compound shows beautifully, if the double bond is shifted to center, this goes to here, so you will get a resonance structure of this one. Let us say this is structure A, changes into another structure, double bond comes to the middle, this side minus, this side plus, this you call it as a B. If the double bond goes in this direction, opposite direction, you will get one more resonance structure which is almost equals to that, but charges are, now this side minus will be there, that side will be the plus charge will be. Conceptually, the structure C and structure B are nothing but same, in fact minus and plus ulta. But if there is a group like a methyl group, some group is there, then these two will be different. A group containing positive charge, a group containing negative charge will be different. So, if this group is not there, B and C looks identical. We think A and B are okay resonance structures because this is neutral, that is plus minus something different. So, that is resonance structure we accept. But if A gives C means C and A, B is nothing but same, see, positive charge, negative charge only, right side, left side. Shall I consider this as another structure or same structure? Means no. It is different structure having the same features, that is all. If I put a group like a methyl or ethyl or a phenyl group here, then you can realize a group with negative charge, a group with positive charge are different. So, therefore, finally, what we have to accept is 1,3-butadiene exists in the three forms. One is neutral form without any charge, one is right side minus left side plus, another one is right side plus left side minus. All these three structures goes on changing. Ultimately, you can write there is one structure which is clear, that the 6, that is 4 hydrogens and 4 carbons and hydrogens are fixed. What is uncertain means the double bond positions are sometimes in the corners are there, sometimes in the middles are there. Therefore, this double bond position is changing. So, therefore, let me write like this. Okay. This double bond is uncertain, but the rest of the hydrogens and carbons are certain. So, therefore, this is called what? The plus minus may be go on changing from this end to that end. So, this is called what? Resonance hybrid structure. The theory of resonance we can explain here. Whenever a molecule or ion exists in more than one structure, the definition for the resonance is whenever a molecule exists or ion exists in more than one structure, the phenomenon is called resonance. Such structures, in that structures you can find the double bond position is not at one place, it is moving. See, it is in the terminal, it is in the center, again in the terminal, again in the center, goes on changing. So, this type of double bonds are called delocalized double bonds. Whenever double bond is fixed in one place, the reagent attacks easily. If the double bond is moving, it is called delocalized double bonds or pi bonds. Whenever a pi bond delocalizes, reagent cannot attack. So, therefore, its reactivity decreases and stability increases. Stability increase means its potential energy decreases. So, when you burn this compound, you get some less energy than the expected. The less amount is due to, because when it is formed, formation energy plus resonance energy also released. So, the energy released in the when a molecule acquires resonance is called resonance energy. However, it is calculated indirectly, not directly, because formation energy, resonance energy will be mixed up. You cannot identify only the resonance energy. You can calculate like this. We will show one example. A pentene, when it is added hydrogen in presence of a catalyst, it gives a pentane plus some energy is given out. This E is measured as around 28.6 kilocalories per mole. I am giving just some rough idea. the values are subjected for the verification. So, around 28.6 kilocalories of energy is liberated per mole. Similarly, if a double bond is there like this, without doing, one can say how much energy, same pentane will come. Alkenes are unstable, they are giving this alkanes. So, energy, potential energy decreases, some energy is released. So, you get the same pentene plus 2 into E. This you need not to do experiment also, one can guess, do it or do the experiment, you can verify it is really the E is doubled energy, that is equals to around 57.2 kilocalories will be there. This is verified by theoretically calculation or by practically also. Now, you take another compound, a compound which is having a two double bonds one after the one, that is called alternatively there, which shows resonance when it is added hydrogen, 2 moles of hydrogen will be consumed under the same catalyst influence. What you will get is pentane. Now, what is the expected energy? Expected value will be again 57. Expected value E is equals to, again 2 double bonds are we are hydrogenating. So, around 57.2 we get, isn't it? This is expected value. But what is found is only around 40 kilocalories per mole only, not 57.2. So, why the around 17.2 kilocalories, why less means this molecule when it is formed it started showing the resonance and liberated 17.2. So, that energy is missing. So, therefore, we can show in a graph manner. So, one side let us show the reaction progress on the x axis, on the y axis we are showing the potential energy increase. Always alkenes are higher energy. So, let us take a pentene and a reaction, after the reaction you get pentane. So, when this compound potential energy of this potential energy, when it is converted into the pentene to pentane, some energy is released. This energy is identified as 28.6 kilocalories, right. Now, naturally, if a compound which is having two double bonds, one double bond and another double bond, unconjugated one, when this is converted, you will get exactly double. Exactly double is 57.2 kilocalories, right. But this compound, because it has some resonance which is not giving the 57, but only 40 is giving, only 40 kilocalories is giving. That means its potential energy will be somewhere here. A conjugated system will have the potential energy like this, and from here it is giving this one. So, therefore, only 40 is coming. What about this decrease here? Why it is decreased means it is also supposed to have that much potential energy, but because stabilization through the resonance 17.2 kilocalories it is decreased. The difference is nothing but the 17.2 kilocalories per mole it is released in the when the molecule undergoes a resonance. From here to here it is the resonance energy. So, therefore, first the molecule, not this molecule, however, this cannot show resonance. If this molecule was here, it shows resonance and come down to occupy the better stable position. From there it is converted to this one. So, therefore, around 17.2 it is already released. So, it cannot release once again the 17.2, isn't it? Therefore, only 40 remaining value only it is released, isn't it? So, the difference between that double minus 40, 17.2 kilocalories will be the resonance energy of this particular, this compound has a resonance energy is equals to 17.2 kilocalories was given as a answer. This is all per mole. One molecule you cannot take and go for the calculation. 1 gram mole or Avogadro number of that molecules can be taken and done the experiment. So, therefore, it is studied that this molecule is more stable, its potential energy will be less than the expected one. So, because of the resonance phenomena. So, the first property of the alkadienes is resonance stability. So, we were doing the properties of alkadienes. So, first property finished. Second property, 1,4 addition. 1,4 addition. This is what a special property of the alkadiene. If a double bonded system, if twice are there, let us add the bromine excess. What happens, you see? Excess of bromine dissolved in CCl4, if it is added, one set of bromine on one double bond, another set bromine on the second double bond. So, you will get 1, 2, 3, 4 tetrabromo butane will be formed. For this, no query, that is no doubt to understand. So, each double bond consuming the bromine. So, tetrabromo butane is formed. It is a very clear observation. But if this compound is treated with only 1 mole of bromine, then what happens? 1 mole means either of this double bond will be consumed. So, expected product will be 1 double bond will be restored as it is, CH2CH. 1 double bond is consumed, 1 bromine. So, therefore, I expect this answer. This is what my expected answer. And in fact, in the practically what happened is, this expected answer is found to be only 20%. And 80% was observed some other product. What is that some other product? 1 bromine was added on the first carbon, another bromine is added on the last carbon, double bond is shifted to center. Hydrogens are as it is, but the double bond position is shifted to center. Bromines are added on the terminals, the double bond is found to be in the center. This is unexpected product. This you can call 1,2 bromo. This is 1,4 bromo, isn't it? 80% major product gone to the unexpected product. How you got this unexpected product? What must be the mechanism of this product? I have to explain now. First one is, let us see the bromine splits up into Br plus and minus. Out of Br plus and minus, first plus will attack because it is a electrophilic addition reaction norms, first electrophile, step 1. So, Br plus will be added. Where it will be added means one of the double bond, let us cornerize, and on that it is attacking. Out of this also, will it go on the first carbon or second carbon? Means we have a rule called Markovnikov rule. In this rule, minus party adds where hydrogens less. This side 2 hydrogens are there, this side 1 hydrogen. So, minus party adds where hydrogens less. That means plus goes to the more hydrogen side. So, according to the Markovnikov rule, so the Br plus goes to the terminal carbon, leaving the carbocation here. So, this is your intermediate, right? Let me finish off with hydrogens. This should be the intermediate 1. If this intermediate 1 participate in the Br attack, that is second step. This is step 1, right? Step 1, step 2. In the step 2, Br minus is attacking on the carbon. So, therefore, this answer is found. So, the answer 1, or let us say answer A, explanation is somewhat easy. Just only thing is Br plus terminal carbon. Even Br, if you add here, Br second one you add also, you will get same. But let me, according to the procedure means electrophile will attack, not the dot. Br plus will attack, that goes to the terminal carbon and making the 2 degree carbocation. and on which Br minus adds. So, therefore, this answer A comes, that is the expected answer is over. Now, the how come this another answer B, where from this B is formed means now this intermediate 1, let me call this intermediate 1, changes not participate step 2, but undergoes a resonance phenomena. This is what observed in the allylic also, like that, but that was free radical, this is the carbocation. So, the double bond shows a resonance now. So, the double bond A goes to the middle, but the carbocation comes to the terminal one, right. Now, on this if the step 2 takes place. So, step 2 is not taking place on the intermediate 1. Intermediate 1 changes through resonance intermediate 2. Then intermediate 2 is undergoing a step 2, that is Br minus attack. Then it is giving the 1 and 4. This 1 4 is not only the number of the carbons. If the compound is very big also, we say 1 4, because with reference to the electrophile added carbon, nucleophile added carbon is 4th carbon. Therefore, I call this is a 1 4 addition product. B product is called 1 4 addition product. I call the product A as a 1 2 addition product. 1 2 addition product, 1 4 addition product. I expected only the first one, actually bromine is added and the reaction over, but I got another product which is a major one. This is because of the intermediate 1 changed to intermediate 2 and then participated step 2 and B is formed. Now, the question is why this should be the major, why not the first one is major? Then we observe the stability of the intermediates and the products here. In fact, if intermediate stability, if you do, this is 2 degree, this is 1 degree only. See, 2 degree must be the more stable one. So, therefore, this should be the major one. But here intermediate stability is not the criteria, it is the product stability is the criteria. In the product A, how many hyperconjugations are there? Only 1. So, 1 hyperconjugation versus how many hyperconjugations this side 2, that side 2, 4 hyperconjugations. So, what is the ratio? 1:4. That means 20% and 80%. Logically, from the theory also you are getting the same thing. 1:4 means 1 by 5 into 100, 4 by 5 into 100 is 80%, isn't it? So, how beautifully the 80% formation is explained by the theory here and backed by the beautifully this mechanism. So, the how the B is formed means the intermediate 1 is not directly participating in step 2. Intermediate 1 changes to intermediate 2 through resonance and then undergoing a Br minus attack, thereby it is giving the 80%. Out of curiosity, the reaction was conducted at little slightly above temperature around 40 degrees centigrade. We got this results actually, not at 25 in fact. But out of the curiosity, some scientists observed that the temperature of the 40 is going on decreasing. Then what happened is this 20% is becoming more, 80% is becoming less. Out of curiosity, further decreased, established at minus 80 degrees centigrade. At minus 80 degrees centigrade, this 1 2 addition product is noticed as 80% and 1 4 addition product is noticed as 20%. Not only major minor, but exactly reverse percentages were observed at minus 80 degrees means very cold condition. 20% product has become 80, 80% has become 20. That means 1 2 addition is become major. Why it is so means as the temperature decreasing, the resonance is not taking place. Why? What is the connection between temperature and resonance? In the resonance, electrons are moving, isn't it? A movement requires energy. So, energy you are controlling, cut shorting. So, as the temperature decreasing, the molecule without showing resonance opens up, becomes addition, electrophile adds, nucleophile adds and answers is giving. Instead of resonating and giving the another intermediate, without second intermediate, first intermediate is working well and then giving the answer. So, as the temperature decreases, the A is percentage increasing. So, the product A is called that is kinetically controlled product. As the temperature decreases, the rate of reaction decreasing, that is resonance is decreasing, and then this is called kinetically controlled product. At room temperature or 40 degrees, this is more stable. More stable means thermodynamically this is more stable. So, the B is called thermodynamically controlled product. A is called kinetically controlled product. Okay. If the reaction is kinetically controlled, A becomes major, B becomes. If the reaction is thermodynamically controlled, B becomes more. It is also studied if the solvent is polar. Polar means resonance encourages. So, the B percentage increases. If the solvent is non-polar, then the resonance will not be entertained. So, simple additions takes place, and 1,2 addition is in the non-polar solvent, 1,4 addition in the polar solvent. Solvent effect also well studied on this reaction. Similar to this bromination, you can go for the addition of HBr, addition of other products like AB additions you can observe on this reaction. Especially catalytic hydrogenation has got one more the implication or one observation. Let us see that. A butadiene is treated with the hydrogen gas in presence of a catalyst like nickel and palladium platinum and heated around 200 degrees centigrade. The hydrogens are being added to the alkene, right. So, how many means if excess of hydrogen is added, NF, then 2 hydrogen, 2 totally what happens, so a set of hydrogen and one double bond, another set and another. So, we will get N-butane formation. For this, no more discussion, because 2 double bonds are there, excess are added, both are consumed. So, 1,3-butadiene becomes into N-butane. This is called excess of hydrogenation. So, leads to total saturation. But all the problem is with 1 mole. 1 mole of only hydrogen. So, pressure can be controlled and you can do this type of the controlled addition in presence of the catalyst only, like nickel or something. So, 1 mole of hydrogen if you add, what happens? 1 double bond will be restored, isn't it? Only 1 double bond will be undergoes addition. That is what the 1,2 addition product. Here also you will get one more the answer. The 1,4 addition product is also observed in this case also, and happens to be the major one. Now, can we calculate the percentage of the major minor means? In this case, it is 2 hyperconjugable hydrogens. In this case, 3 plus 3, 6 hyperconjugable hydrogens. That means 2:1, 2:6, 1:3. That is 1 out of 4 into 100 is 25%. So, first one is 25%. Second one is 1 out of 3 out of 4. 3 out of 4 into 100 is 75%. That means this is 75%. That is 25%. So, still it is major working well. So, the theory says that it has more hyperconjugable hydrogen, therefore, 1,4 addition will be the major one. To an extent of 1:3 or 25%, 75% will be the answer, right. But the mechanism, if the point comes, we have a small problem here. Br addition is, bromine addition is Br plus, Br minus, electrophile, step 1, intermediate carbocation and Br minus, that is the mechanism. But how the hydrogenation mechanism means, we have seen when ethylene is treated with the hydrogen gas, right, we are getting a ethane CH3 and CH3. For this, what exactly the mechanism means? On a particle of nickel, on a particle of the nickel particle, the mechanism is explained like, on a nickel particle, ethylene is adsorbed, hydrogen is adsorbed and slowly the bond formation taking place. First this a new bond will be forming, simultaneously the old bond will be breaking. So at first you find a 4-membered ring formation, and then the old bond will be totally disappear, new bonds will be formed, then the molecule will come out. So this ethylene and hydrogen adsorbs, then comes out, that is called desorption, adsorption and desorption. These phenomena gives our the explanation. So ethylene, hydrogen adsorbed and reaction takes place and comes out. Now can you propose for this there is no problem, on a nickel particle this adsorbed, hydrogen adsorbed and reaction. But here hydrogens are isn't it, if I propose like this, on a nickel particle the butadiene adsorbs and side by hydrogen adsorbs, and then the reaction taking place means this is something wrong here. The bond is shown long bond and then showing, so this is totally theoretically wrong. Okay, this is not correct. In fact, the butadiene is not a straight one. Ethylene is a straight molecule, but here there is a 2 angles are involved. So butadiene, really speaking, it exists in the 2 forms. So 2 double bonds may be in the same side, that is with reference to the hydrogen here, the 2 double bonds are same side. With reference to the single bond, the 2 double bonds can be opposite also. So 2 types of butadienes are existing. There will be fast exchange also taking place with reference to the rotation of CC bond. Now can I ask a question, what is the relation between this X and Y? X is a cis type containing, Y is a trans type containing. So we think they are geometric isomers, but it is wrong, because I said already a single bond rotation gives that one. A double bond rotates, single bond rotates, the double bond comes this side. So they are conformational isomers. X and Y are conformational, but not 100% conformational also, because this single bond is not always single. Many times this resonance comes in between, double bond comes. So it is not as rotatable as in the case of ethane. This bond has got some problem of not rotating properties there. But still, if these 2 clear isomers are written, we have to show that this is a conformational isomerism, and X is called as a S-cis or cisoid. Cisoid 1,3-butadiene. The Y is called as transoid. Transoid or S-cis, S-trans, single bond trans, isn't it? Generally cis and trans are double bond oriented. Now with reference to single bond, 2 double bonds are same side. With reference to single bond, 2 double bonds are up. S-trans or transoid 1,3-butadiene. Now to show the reaction, we are taking only cisoid butadiene. Now the explanation of the addition reaction will become easy. You take this is a nickel particle on which hydrogen molecule is adsorbed. Okay, butadiene is adsorbed, cisoid butadiene. Then the reaction is taking place here, and the old bond is ceasing here. This is disappearing, this is disappearing. A new bond is forming here. So what comes out after the reaction means a double bond is formed in the center. Okay, and hydrogen is added here, hydrogen is added here. Now I ask, can you name the product called, what is the product called? Means strictly speaking, this is cis-to-butene. Where from the cis means with reference to double bond, 2 methyls are same side, isn't it? So it is a cis-to-butene, almost 90 to 100% you will get the cis-to-butene. 90 to 100% means highest the percentage of cis is. Why not the trans is formed? In fact, if somebody asks cis and trans 2 butenes are possible, this is 2 butene, is it? 2 butene can be cis or trans. Which is the major means we go for trans, because trans is more stable. But in this case, if the mechanism clearly shows that cisoid only if I take, you will get it. But if I take transoid, that means double bond, one this side, one that side, isn't it? Then hydrogen, how can I absorb? One hydrogen there, one hydrogen here, such a long you cannot. So transoid cannot be taken and explain the mechanism. Only cisoid can be taken and explain the mechanism. Therefore, the formation of cis is the theoretically expected. Even in the practically also, if you do, it is the cis tubutin only will be formed. Okay. So, it is verified. That is why the butadiene, when treated with 1 mole of hydrogen, you will get almost 90 to 100%. 2 cis, that is cis tubutin will be the major answer. So, this is what 1,4 addition. So, let us go for the another property called Diels-Alder reaction. In this reaction, a butadiene is written in this particular pattern, simplest reaction. With ethylene it is reacting. So, ethylene reacts one here, the double bond change, almost like an extension to the 1,4 addition. But in the 1,4 addition, we have seen it can be a electrophile nucleophile, or in the adsorption phenomena simultaneous addition. In this particular addition also, it is not exactly the plus minus attack. The reaction mechanism, if you the conditions and all that, if you carefully observe, the reactions are not catalyzed by the acid sign bases. They are not encouraged by the polar and non-polar solvents. They have a high stereochemistry of containing the that is light forbidden or the thermally forbidden. All that cases stereochemistry, carefully observe that there is a lot of chemistry you have to read. However, let us brief it and see that the reaction either by the thermal or by the photolytically, the reaction goes in a cyclic pattern and you will get the cyclohexene formation. Okay. So, in this reaction, the reaction is observed very around 10% reaction taking place, cyclohexene is formed. But if the this ene, this is a diene, let us call it as a diene, and this is a diene attacking species. So, people said this is dienophile. So, when dienophile is ethylene, the reaction takes place very less. But if the dienophile is having some electron withdrawing group like a aldehyde, a minus M group, either both the sides or one side at least, the reaction picked up very nicely, and this gives a cyclohexene. This aldehyde will be however intact. So, the product will be, now the reaction has become almost 90% reaction taking place. Because of this withdrawing capacity, the dienophile activity is increased and said to be a good dienophile. Good dienophile. Similar the case, if the compound is having a double bond on the both the sides, see minus M groups are both the side, and it is tied up also. So, sterically there is no hindrance also. So, the reaction takes place really an 100% reaction takes place. In this case, a cyclohexene is formed, but side by there will be an anhydride, let it be like this. So, almost 100% reaction takes place, and this malic anhydride is proved to be the best dienophile when reacts and gives this type of the product. However, these reactions have lot of study later. They have studied under the pericyclic reactions. Pericyclic reactions. Later, they developed into another section of organic chemistry. In fact, the lot of chemistry is identified behind this reaction, in fact. But this is a brief study, however. So, let us go for the another property called polymerization. As we have seen already, a vinyl chloride undergoes a polymerization to give the polyvinyl chloride, which is a plastic. The plastic has got a number of advantages, just like a plastic scale will have a very good flexibility, light, water resistance, and long durability and transparency, and so many features we can observe in the plastics. but they don't have a elastic property, right? But whereas a butadiene, for example, we have a natural compound having a 2-methyl this is nothing but a butadiene, right? It's a 2-methyl extra. This is called commonly isoprene. Isoprene, when polymerizes, it gives a polyisoprene. In fact, the double bond is shifted to center and the methyl will be there, let it be like this, but n number let us write. This is called polyisoprene. Polyisoprene is commonly known as nothing but the natural rubber. The rubber, you know that very well, it has got the one unusual property, what? Elastic property. The elastic property to this particular product is not there in the normal plastics. So, alkenes on polymerization gives plastics, alkadienes on polymerization gives the elastic compound, that is rubber is the product, right? Now, how come this elastic property, if you see, with reference to the double bond, the compound, if it is like this, there are so many double bonds are there in between the chain, yeah, right? So, at every double bond, the compound is cis type, and this double bond is again a cis, that side one side, this side one side. So, the molecule goes on like this. When you stretch it, the cis pattern is very, very essential. It is also studied, if sometimes polymerization gives a trans product that is not having elastic property. So, elastic property is due to the cis orientation of this polymer. So, the polyisoprene, when you write cis type, that means at every double bond we have to quote that this methyl group and the remaining, that main compound, the same side hydrogen, same side going. You write one more CH2 and write one more double bond. Here now you write methyl and the main compound going in the cis type pattern, see, CH2, here one hydrogen, CH2, a double bond, one methyl group, right? So, like this, the cis configuration is repeated at every double bond. This double bond is cis, this double bond is cis. So, all cis isomer is a natural rubber, in fact. If the cis symmetry is not there, the compound is no more elastic. Structurally, it will be same. On ozonolysis, it will be giving this polyisoprene will cut here, isn't it? You won't get acetone and this one, but it is in continuation with another molecule, isn't it? That means this molecule and another molecule is there. Let me write once again, a double bond and this one, isn't it? This is repeated. So, that means one more structure you write like this. Now, you tell me what happens if I cut in this place, this piece will be the product. This will be an aldehyde one side, a CH2, C double bond O CH3. It is called as what? 1, 2, 3, 4 keto. 4 keto pentanol. So, isoprene on polymerization gives natural rubber on ozonolysis. This is called ozonolysis, isn't it? First ozone treated by the second water in presence of zinc. If I do, you will get this type of the answer. This is to show that double 2 times I have taken, but the main answer is aldehyde one side, a ketone one side. So, it is called 4 keto pentanol. It was initially acid was obtained, that was oxidative ozonolysis, named as a levulinic acid. Later it is named as an aldehyde when controlled reduction doing the ozonolysis. Reductive ozonolysis gave an aldehyde, that is called 4 keto pentanol or levoaldehyde. So, that shows to confirm the structure. So, the cis and trans will give the same this compound, but orientation is different. To get the cis outside the lab, in the plants how they are preparing, that is biologically enzymes are controlling, but outside the cell how we can prepare this all cis isomer, that is the natural rubber. It is again a task that was achieved by the 2 scientists using the titanium tetrachloride plus trialkyl aluminum. This particular catalyst was introduced by the scientist called Ziegler and Natta. They used this a solid heterogeneous catalysis, they conducted, and thereby the alkenes orientation was stereochemically controlled, and they could able to get all cis isomer intact, and that was the secret for the achieving this the natural rubber preparation outside the cell as it is with the same elastic property. They got it back, and they won a Nobel Prize for the introduction of this type of the heterogeneous catalysis controlling the stereochemistry of the polymer. That catalyst is known as Ziegler-Natta catalyst, titanium tetrachloride trialkyl aluminum. Here the alkyl group in fact it is a replacement of this monomer will be there. This alkyl will become into isoprene, isoprene will go into exchange reaction, controlling pattern of the stereochemistry will be there, and that gives the cis isomer of this one. All the cis isomers only will have the elastic property. So, one direct question is alkenes on polymerization gives plastics, alkadienes on polymerization gives the rubber which has got the elastic property.